for an introduction, background on the product, a timeline of the year, some things that we worked on, and splitting it up into different tasks for physical and electrical, and then some conclusions that we came to accomplish. Starting off, and I'm working on mostly SolidWorks and design, also keeping everything organized and materials.
And I took the lead with the library programming, and I also took the reins for the schedule planning and just kind of seeing the different projects and also the presentation of the issues for the costs and stuff.
For me, I kind of worked on the manufacturing aspects of the project and also just the operation of the rig.
Right, so going into our background, so helicopter airframe experience high vibrations due to their rotor blades. So when that decreases comfort and increases wear of systems inside the helicopter, there are devices called vibration dampers, which are installed through the rotor blades on helicopters. What they'll do is they can sense a vibration from a helicopter and generate a counter vibration wave, which will cancel it out, equalizing the vibration inside the cabin to make it more comfortable. Current vibrating dampers on the market are electrically powered, meaning they're heavier and have slower response times. Our design is hydraulically actuated, meaning it can be linked directly to the helicopter's built-in hydraulic system. That's going to save size and weight. This right here is a diagram of the system operation. We have a beat of vibration, generate a counter vibration wave, which will cancel it out and result in so our goal last year's team was able to successfully manufacture the rig, and they were able to conduct some preliminary tests. One of the main goals is to make actual force of plus or minus 400 pounds force. Last year's team was able to get about 140 pounds. Also, to be able, they were able to successfully control it between 20 and 30 knots, where that's about the frequency coming from the rotor blades of the helicopter. And also, our goal is to implement a new mass design, which is going to reduce the rig size to about 1 foot square or less. So again, going over stuff from last time, they were able to reach about 140 pounds force and have a reaction time of sitting still going to plus or minus 50 pounds in about 7 seconds. And there were only several tests performed last year, so there was a lot of testing that needed to perform to figure out what issues are causing them of not being able to reach that 100 pounds force or have that reaction speed.
Going over the timeline quickly for the fall. In September, there's a lot of conversations with our sponsors, just understanding what we need to do, and then also as a team, just understanding the project as a whole. Moving to October, we did some rig modifications, and then beyond that was more just testing the rig. January is again looking at the data. February was coming up with some new ideas of how we could fix some problems that were happening with the rig. And then March and April is just working on the rig, updating it to its new design, and then also fixing those issues that we're having.
So going over the entire system itself very briefly on how the system operates. So firstly, we have it's outside vibration actuator, which takes inputs from a computer module, takes those inputs, forms into a command wave, takes that command wave and makes an actuator move up and down linearly. By that, a absorbed mass in the center vibrates at that frequency that's set by the command wave. And in addition, Hall sensors and accelerometers take both the displacement and the acceleration of the system itself, puts it back into the computer for post-data analysis, as well as puts it back into the system so it can run and correct itself while it's doing the testing conditions. So a little bit more on the technical side of how it works. There's a lot of different variables that goes into the system. I won't name all of them, but it's things like the frequency, the acceleration of the system is trying to reach, the displacement that's trying to reach, as well as Ka and Kd. Ka and Kd are essentially error gains or error corrections, which in the equation down below, the current is equal to the acceleration and the displacement, where we have the commanded acceleration and then whatever we're trying to achieve. There's a lot of trying to see correction based on the inputs from the tests. And then looking at the graphic, Ka controls the amplitude of the wave, while Kd is the displacement, and that's the midpoint of where that sine oscillates. Lastly, with the LabVIEW interface, there's about 4 different sections. The first section is split up to do the command and separate, which is the data collection. The second panel is to actually save the data. The third panel is to monitor the system with the accelerometer and all the readings. And the fourth one is to set the parameters from the command. You can see here in the image on the right, this is the system in action. On the bottom right-hand corner, you can see that it's generating a sine wave with an accelerometer with an input with the sample rate on that top.
One considerations that we took into account before we implemented the design rate was we wanted to make sure that the mass or absorbent mass of the system was the same as the original design. So we had to make calculations to that, and then also making sure that our mass is still give the correct natural frequency based on our weight, because if we are able to hit that natural resonant frequency, it's going to increase our force output by a lot. Also, making sure that our acceleration and displacement will actually make our mass hit the bottom or top plate of our rig. Something we implemented we now see new hydraulic lines and gear valves. So we have this implementation of smaller hydraulic lines that decreases the amount of fluid volume that has to be into the actuator piston. That's going to decrease heat, and the implementation of dual gear valves allows us to bleed all air out of the system before the test, which will help us increase the reaction time of the system.
So the very first test, we wanted to do a parameter test to see what we would get when we ran the rig test. On the top left-hand corner is some of the parameters that we use, such as a frequency of 5 hertz, as well as a sample rate of 5,000. Circled on the graphic, some of the results that we got towards the end, with the higher further on to the time. The data didn't really look great as it became unstable, as well as the acceleration up at the top. It didn't match the command that we're trying to get to. If we're trying to command 5 Gs, we want to see 5 Gs command at a total very late long. So we had some issues persisted further in the hydraulic.
So one of the issues that we're having with the system is that the spring in the mass was at an angle for some reason. We believe it's because the springs, when you put them on a table, they weren't machined completely flat. So to fix that, we're gearing up with custom epoxy bolts. And so we shimmed the spring straight, and we put them in the system, and we did more tests. That kind of helped with the error, the angle a little bit. Okay, so another issue that we're having with the actuator was actually at an angle. So you can see before we fixed it, it's touching the bottom plate there, and it's also at a 0.4 degree angle. So if you can imagine, it's at 0.4 degree angle at the bottom, but if you go up a couple inches, say like 10 inches, it's be off way more than just 0.4 inches. So we ended up shimming the actuator at the bottom to around 0.05 inches, which reduced a lot of error that we were seeing when we were running the rig. Additionally, to fulfill one of the requirements set by the sponsors of having a 1 foot cubic volume space, we redesigned the center mass along with machined new spacer sleeves, which are those rods on the ends, and that allowed us to shrink the rig down from 15 inches down to around 10 inches.
So going into the LabVIEW stuff, I won't go too much on this, but one current issue that we were facing was that during our data iterations, we weren't achieving the sample rate that we were set to achieve. So we had 5,000 samples, we got about 600 samples. Why that's an issue is that during data testing, as we see on the bottom graphic, a lot of spots within the sine wave are blank or missing. Those data points can be crucial and could be valuable to figure out what's happening with the rig itself. It's not achieving our command 5,000. So a couple of solutions that we came up with was to separate the calculation loop from the acquisition loop, adding additional data exports to account for the filtering, as well as adjusting the command and separate from 5,000 to some other number. For easier to understand, the LabVIEW itself is isolated into 3 different sections. The first section is the sensor data, so anything from the accelerometer and all that's considered are sent to the LabVIEW via these data boxes. This green box in the center is where the calculation mechanics happen, and the red section all the way at the end is what is the data that gets transferred through the PC to do some iterations for the post-processing as well as the feedback. So later on, I was able to separate the calculation from the acquisition fee. This helps to kind of offload some of the work in the system itself and achieve a much better sample rate. So it doesn't have to export the data to a PC overflow system, essentially using the data. Additionally, with the X3, we found out that it was only reporting the filtered version of the multi-sensor data using a low-pass filter. With the new LabVIEW data, it now exports both X3 and XF, as well as inputs for if the system is filtered on or off. As you see here, on the low-pass filter, for those who don't know, anything with a low frequency is able to pass, and high frequency is not able to pass. So the circled portions are X3F and X3, while the rightmost column dictates whether the system is using the filtering data or not. So now our final or most current test. So with this test, we use two different sets, one with the new shims that we designed, and the other one using both the new shims, UVI, and also the adjusted frequency. On the top graph, you can see that we were about 10 Gs small from the commanded. And on the bottom graphic, that green line represents what we want the system to achieve. When we command 60 Gs, you'll get 60 Gs. And our most aggressive test with this parameter is that orange line that you see. The reason why there's a difference is due to proof of friction, where two surfaces are rubbing against each other, and due to that, it loses acceleration when moving. Additionally, with the sample rate, just so visually you can see, the first test we began about 60 samples, and then after the month of pages, we got around 650 to 900 samples, close to 1,000 for other iterations as well. And then comparing it to last year's data, they were able to achieve 7 seconds for the from base to peak amplitude, while we were able to achieve it in 5 seconds.
So when we're going to build materials in 2026, it's split up. There are many miscellaneous lab supplies that we have to order. Also, the hydraulic system looking into that. For reassembly, there are new hydraulic lines, and also new sensors to put higher key accelerator operators down for future tests that go over 50 pounds. And that gives us a total spend of $3,000. So main accomplishments are shooting resize from 15 inches down to 10 inches. This fit that 1.3 box. Also choosing the hydraulic lines that 2,000 guarantee that there's no error in the system. Spring straightening molds and also shifting the actuator at the bottom to make sure our system is as straight as possible. Improvements to the lab code. And of course, increasing our force generation, where this year we were able to achieve about 200 pounds force, which is 50 pounds higher than last year's team. Faster reaction time, 2 seconds faster. Some future goals for next year's team is going to be manufacturing like we found also creates the balance in our system. And before we test the new design that is intended design, we hopefully be able to reach that reaction speed and higher force output. Any questions?
Can you go back to slide 16 for a second? What is your x-axis?
X-axis should be the time. So
Okay.
for both of them, it is the time axis. So over time, we'll directly relate to the amount of timestamps for both the acceleration.
Okay. Do you have any recommendations for next year's team for upping the force out?
One idea that we have is also concerning the hydraulic lines. Well, we did shrink the diameter of the hydraulic lines. The current lines are about 32 inches long, and we're thinking about shrinking them to around 20 to 22, making less time to travel for the hydraulic fluid to travel in the system, which should hopefully increase the response time.
Did you discover the gains analytically or experimentally for Ka, Kd?
So Ka and Kd were found using a different testing set. So they're denoted as test A and B, But test A is manually moving the lifter plate up and down while only using the Hall effect sensor data. And then test B is similar to our heart rate system when we're testing full springs and masses. But from test number A, we're able to find the approximate adjustments for KA and KP.
We also use MATLAB as well to find these values. So it kind of is verified with situations.
Any other question, guys? No question, thanks.
Next is ECT, who's going to be presented by Zach.